All right, picking up where we left off yesterday, we're going to talk about our last example of a single displacement reaction. So a reminder, in a single displacement reaction, one element is switching places with another element of the same type that's in a compound. So in this case, halogens are displacing each other. Halogens is that group 17 on the periodic table, that highly reactive group, and they are more reactive than whatever element is below them in their group. So for example, fluorine is more reactive than all the elements underneath it because it's the most reactive. And then chlorine is not more reactive than fluorine, but it is more reactive than any halogen that is underneath it on the periodic table. And then bromine is more reactive than iodine and the ones underneath it, and so on and so forth. So they can replace each other in reactions if they are more reactive than whatever halogen is already in the compound. An example of this, if you put chlorine gas into the potassium bromide, into solution with potassium bromide, then you would have that chlorine replace bromine because it's more reactive than it, and as a result you'd end up with potassium chloride and then liquid bromine instead. Okay, so it's just going to zip in and replace it. For those of you who were not here on the previous day, we are going through lots of different examples of each type of reaction. I don't expect you to remember all the individual examples, but the point of having so many examples is so that you can see that while these two reactions that are on the screen look different from each other on the surface because they have different elements, different things are happening, they are the same format. The structure of the equation is the same. We have one element replacing another element in a compound, and we wind up with an element in a compound with the new element in that compound instead of outside of it. So it's just replacing it. Now let's talk about a step up from single replacement reactions. These types of reactions are called double displacement reactions. In a double displacement reaction, what happens is instead of one element displacing the other one in the compound, replacing it and kicking it out, they just swap places. So when they're in an aqueous solution, an element from one compound will go into the other, and the element that leaves that compound will go into the original compound. And you'll have two new compounds where different ions have swapped places with each other. It follows the general reaction AX plus BY yields AY plus BX. So you can see, didn't mean to tab up. I was trying to start my drawing tool. You can see that the Y swapped into this position and the X swapped into this position. So they just switched places. That's all that happened. A, X, B, and Y are the reactants represented ions. So these letters just represent different ions. And then A, Y, and BX are going to be ionic or molecular compounds that then are going to change into new compounds at the end. There are several examples of double displacement reactions, and we'll go through a few of those examples so you can see what this looks like in a real reaction. So let's look at one of those examples. The formation of a precipitate. So this is what happens when one of those new compounds that's created through a displacement reaction is insoluble or only slightly soluble, meaning it either doesn't dissolve at all or it just dissolves very little. And so as a result, you get a solid that forms in your liquid, okay, like we did during the lab when we had that sort of blue gel-looking substance form in the water. That was a precipitate. An example here would be potassium iodide and lead nitrate. So if you have dissolved potassium iodide and lead nitrate in a solution, what will happen is the potassium will attach to the nitrate and the lead will attach to the iodine. So they will swap places. And the resulting lead iodide is not soluble. So instead of remaining aqueous, it will go solid in the container, and you will see it precipitate out of solution. The potassium nitrate, however, remains soluble, so it will stay dissolved in the solution, and you won't see it come out of solution. The Pb2+ and the negative iodine anions are very attracted to each other, which is the reason that this occurs. So when you have ions in solution, I want you to remember that if you have this big solution of ions, it's not as though the K and I ions are together over here and the lead and nitrate ions are together over here and they're floating around together. What really happens is you'll wind up with just loose ions. So you'll have a positive potassium ion floating around here and there, and a negative iodine one floating around, and a positive lead one floating around, and then of course the nitrate ion will stay connected because it's covalently bonded, but it will still have a charge on it, so it will be floating around in solution as well. And so what happens is when all of these are dissolved in aqueous solution, these two get really attracted to each other, and so then instead of staying dissolved in the solution, they bond to each other, form a solid that's not soluble, and precipitate out of the solution. The potassium and the nitrate ions stay in solution and they never participate in the reaction. So you will often hear these types of ions referred to as spectator ions because they're just going to stay happy and floating around in the solution, and the only way you would have them solidify into a compound would be if you evaporated off whatever you had them dissolved in. Otherwise, they're just going to stay happy floating in the solution, which is why we call them spectator ions. The next thing that can happen is the formation of a gas. So just like we can form an insoluble compound, what can happen is one of the new compounds that can be formed is a gas, and it's a type of gas that doesn't dissolve easily in whatever you have it dissolved in, and as a result, it will bubble out of solution. Okay, so an example of this would be if you took iron sulfide and combined it with hydrochloric acid in solution, the result would be iron chloride and then hydrogen sulfide gas. And hydrogen sulfide gas is not easy to dissolve, so instead of staying in solution, it would bubble out of the liquid, and you would see the production of a gas happening. And then the other thing that can happen is sometimes when ions switch places, one of the new substances that's formed is water. So obviously, if things were dissolved in solution, you wouldn't see that the water was produced, but it can happen. So if you combine hydrochloric acid and sodium hydroxide, what you will get is sodium chloride, which is table salt, and water, and it will stay dissolved in the water because salt dissolves in water. So you may not see that, but you can leave it and the water will evaporate off, and you'll be left with just table salt in the container. This is a double displacement reaction, but it's also a specific type of reaction called a neutralization reaction, where you take an acid and a base of equal strengths and you combine them and they neutralize each other, meaning they are no longer acidic or basic, they're neutral. And the result of a neutralization reaction is always a salt of some kind and water. So we'll talk about neutralization reactions again if we get to the chapter about acids and bases this year, but neutralization reactions are also often double displacement reactions. So. All right. The last type of reaction we need to talk about today is a combustion reaction. A combustion reaction is when a substance combines with oxygen and releases a large amount of energy in the form of light and heat. There is some examples of it, like burning natural gas or burning propane or burning gasoline or burning wood, but there's no general reaction for a combustion reaction. The way you can tell a combustion reaction is happening is you have oxygen combining with some substance, and when you introduce a small amount of energy to start the reaction happening, then a large amount of energy is released. So think about the last time you made a campfire, right? You put wood on the fire. If you have difficulty setting fires, maybe you put lighter fluid over the top of the fire, and then you introduced a small amount of energy, right? Like a match or a lighter or a spark of some kind. And that tiny amount of energy is nowhere near compared to the amount of energy that the campfire put off, right? That is an indication that you are experiencing a combustion reaction. That large release of energy and light, that is your biggest indicator that a combustion reaction is happening. And if you can put out the combustion reaction by smothering it, removing oxygen from the equation, then you know for sure it's combustion, okay? So that's why when you put a lid over a candle, it snuffs out. If you throw a blanket over a fire, it can help put it out, because what you're doing is depriving the combustion reaction of oxygen, which is required in order for the reaction to take place. So here's an example for you, C3H8, which is some kind of fuel. I'm blanking on what it's called right now. I think it's like propane or butane, one of those. And then oxygen yields carbon dioxide gas and water. Okay? Now you're saying, that's weird. When you burn something, it produces water? Yes, it does. But it produces it in the gas form because of all of the heat and stuff that is happening in the reaction. So you're not going to see the water. Okay? The CO2 is part of the reason why part of the reason why it's dangerous to be in a building that's on fire, okay? Because not only is it removing oxygen, but it's producing carbon dioxide, which your body cannot use to breathe. And then also there's things like smoke inhalation that also make it dangerous as well. But there we go. Okay, that is the end of the notes.